This is the final of a series of 6 videos which try to explain something of the Higgs field and the way in which it can give mass to the known elementary particles. Someone who's studied mathematics and physics to around the age of 20 or who is reasonably familiar with most of the ideas shown here should be able to work through the arguments presented in the 6 videos so that they end up with some grasp of the sophisticated concepts involved without having cut too many corners. A lot of new ideas have needed to be introduced, and although those ideas are no more difficult than the concepts shown here, they will require a good deal of work if they are to build up to a coherent understanding of the Higgs mechanism and to try and understand what's really going on. In this, the 6th video, I want to show how the presence of the non-zero Higgs field left over after symmetry breaking can be thought of as giving mass to the fermions. In previous videos we've looked a little at the standard model of physics and the particles that it deals with. These can be summarized in this table. What might be called the matter particles, the stuff of nature, are particles with spin 1/2, and they're called fermions. We can break these down into 2 basic groups, the quarks and the leptons, but these each break down into 3 families, and we've looked at some of the various distinctions between these within families and across families. All of these fermions can interact with one another in various ways, and these interactions come about from the family of what we might term the force particles or the exchange particles. These are particles with spin equal to 1, and they're called the gauge bosons. There look to be 4 families with different numbers of bosons in each of them, but they are responsible for only 3 types of force between the various fermions. The gluons, 8 of them, are the force particles for the color charge of the quarks. Only the quarks. The photon is the force particle for the electrical charge, any electrically charged particles. That's all the quarks and some of the leptons, the electron, the muon and the tau. The W+, W- and Z0 bosons are the force particles for the weak charge. The W+, W- are responsible when electrical charge is also being swapped in some way, whereas the Z0 is responsible for electrically neutral or no charge situations. The weak force, whether from the W's or the Z, can be felt by all the fermions in the table, at least those with spins that are left-handed, but we'll say more about that later. We said that the Higgs boson is something of an add-on and comes from the Higgs field after spontaneous symmetry breaking of the field. After that spontaneous symmetry breaking, a particular type of oscillation of the field, what we called radially in the valley, involves potential energy going up and down and therefore represents a particle with mass, the Higgs boson. However, the Higgs field also makes an important contribution to the standard model. The issue we were concerned with last time was with the fact that the weak gauge bosons, the W's and the Z, are predicted by the model to have 0 mass, and yet in practice they have considerable mass. The Higgs field came to the rescue of this situation by the process of spontaneous symmetry breaking, whereby 3 new massless particles, goldstone bosons, were somehow created from the field when it shifted its value from 0 so that the potential energy could become a minimum. These 3 goldstone bosons came from the oscillations of the field in such a way that the potential energy remained constant. The particles were massless. These 3 goldstone bosons were then effectively taken by the 2 W's and the Z0 to give them mass. That process is known as the Higgs mechanism. In a sense, that is half the job done in explaining what the Higgs field is responsible for and how it relates to mass. The other half has to do with the fact that not only does the Standard Model predict that the gauge boson should have zero mass, it also insists that all the fermions should have zero mass as well. In practice, of course, their mass is not zero. The fermions have a very wide variety of masses. Even the neutrinos, which at one time were thought to be massless, are now believed, from experiment, to have a very small mass and therefore do not travel at the speed of light. So this is our question here. Why do the fermions have mass? And is it again because of the Higgs? That's the question. But I suppose before we can start to try to answer it, we ought to have some understanding as to why the Standard Model predicts that all fermions should be massless. That was our approach with the gauge bosons. We first asked, why does the Standard Model say that they must be massless? Then we accepted that fact, and then we looked at the symmetry breaking of the Higgs mechanism to see how mass could be added to some of the gauge bosons, the W's and the Z, but not, of course, to the gluons or the photon. And that will be the kind of approach we'll take here. We'll ask the question, how is it that the Standard Model insists that the fermions have zero mass? And then we'll ask, how can some quirk of the Higgs field mean that mass can somehow be given to each of the fermions in our table? That's the task. However, there's a good deal of work to be done even to answer the first of those questions about the masslessness of the theoretical fermions before we can move on to the solution using the Higgs field. So here goes. Question: why does the Standard Model insist that fermions have to be described mathematically by field equations and Lagrangians for massless particles? Why are fermions massless according to the theory? Well, the answer is all to do with the spin of the fermions. So let me put some background to that and some general preparation in order to illustrate the need for zero mass fermions in the theory. Fermions are spin-a-half particles and have to be handled using a different type of statistics to bosons, which are integer spin particles. Unlike with our discussion of bosons, fermions can definitely only have two possible spin values of the components of their spin along the direction of motion, whether they have mass or not. This is a general rule of quantum mechanics, that for spin-a-half particles, the only allowable values for the component of that spin in the direction of travel are plus a half or minus a half. Again, this is true whether they have mass or whether they are massless. Here's a simplified illustration of two particle-like fermions travelling from left to right. You can see that they are spinning in opposite directions as they travel to the right. We say that one is right-handed because if you grip the directional arrow with your right hand so that your thumb points in the direction it's travelling, your fingers will point around in the direction of the spin. In that case, we can say it has spin equal to plus a half, and I've shown it with the spin pointing forwards. The other fermion here is said to be left-handed, because if you grip the arrow of direction with your left hand so that your thumb points in the direction it's travelling, your fingers will then point around in the direction of the spin. In that case, we say it has spin equal to minus a half, and I've shown it with the spin pointing backwards. When the spin is right-handed, we say that the spin component is in the direction of motion, and it's equal to plus a half. When the spin is left-handed, we say that the spin component is opposite to the direction of motion, and its value is minus a half. Going back to our table, in many ways the fermions are a mixed bunch of particles. Some of them are electrically charged and feel the electromagnetic force via photons, but not all of them. Some of them have colour charge and experience a strong force via the gluons, but again, not all of them. However, all of them, and I may qualify this in a moment, all of them can be thought of as having some sort of weak charge, and therefore they experience the weak force via the W and Z bosons. Well, the classic example of the weak force, of course, is beta decay. It involves two of the families of fermions, the up-down quark family and the electron-neutrino family. When we discussed this earlier, we used the picture of a down quark in a neutron changing to an up quark with the emission of a virtual W- boson, borrowing energy from the vacuum to produce it, and then returning that energy to leave an electron and an antineutrino. Down to up, giving off a W-, decaying into an electron and an antineutrino pair. Now this might not seem like an interaction in the sense of one particle bouncing off another, but it is, and we discussed all that when we looked at beta decay in part 1. However, there is something strange about beta decay, something that wasn't discovered until 1957. It turns out that all of the electrons that are emitted in beta decay have spin components that are always left-handed. Always -1/2. Always. In fact, it's now known that all leptons, including neutrinos, that are emitted in beta decays are what we call left-handed. Now, as it happens, all antileptons are right-handed, but we still call it a left-handed tendency because we name things by what matter does and not by what antimatter does. Now, the fact that all the electrons, neutrinos or whatever that come from beta decay or from any weak interaction are left-handed should strike you as strange. What I mean is, it's fairly normal, I think, for people to assume that the world does not have any preference for any kind of handedness. We naturally think that there should be no difference between what we see in reality and what we see in a mirror, at least in the sense that what can happen in reality ought to be possible in the mirror situation of it. For example, if you look at the mechanics, the physics of potting a ball in snooker or pool, the classical physics, is fairly straightforward. You can see that after the white ball hits the red ball goes in the pocket on the left, and the white ball goes off in a different direction. If you looked at this in a mirror as it happened, it would look much the same, except that left and right would be swapped over. The red ball would look as though it was going into the pocket on the right. You could then, I suppose, set up another experiment to be exactly the same as what you saw in the mirror. And provided you got the angles and the forces the same, you would indeed get the same result, as far as is measurable. The physics here knows no difference between left and right, and you wouldn't really expect it to. In fact, most of the forces of physics obey that rule. They have what we call mirror symmetry. For example, the laws of physics around the strong force obey that rule. Also, the laws of physics around the electromagnetic force obey the rule too. They know no difference between left and right. The laws are the same. The mirror situation would behave exactly the same as the original situation, except it would be mirrored. However, and this is what's weird, the weak force does not obey that rule. There is a difference between left and right. The electrons and neutrinos from beta decay are always left-handed, regardless of the spin of where they come from. If you set up a mirror experiment expecting them to be right-handed, they still come out left-handed. It's as though the laws of physics for the weak force are only in action for the left-handed fermions. The right-handed fermions don't get involved. The weak force seems to know the difference between left and right. One way to look at this is to say that it is as though the left-handed fermions have the weak charge, but the right-handed fermions don't. The left-handed fermions feel the weak force, but the right-handed fermions don't. Now that's weird. Can you imagine saying that about the electromagnetic force? Imagine saying that electrons with spin in one direction have negative electrical charge and feel the electrostatic forces between each other, but electrons with spin in the other direction are neutral and don't feel the electrostatic force. That sounds bizarre. And of course that's not the case for electromagnetism. But in a way, it is the case for the weak charge and the weak force. All the fermions in the table can be thought of as having the weak charge and feeling the weak force only if they are left-handed. Those that are right-handed are, in a sense, neutral as far as the weak charge is concerned. You might recall that we hinted at this very early on. We were discussing the weak force brought about by the Z0 and the so-called neutral current. If electrons are scattered by protons, then there should be two forces in play. There's no question of the strong force being present because electrons don't feel the strong force. The only two forces involved between electrons and protons are the electromagnetic force and the weak force. Electrons can partake in both electromagnetic and weak interactions, and protons, because they're made up of quarks, can also take part in electromagnetic and weak interactions. If we look at elastic electron-proton scattering, that means where no particle changes take place, they just scatter, then the Feynman diagrams would be these. Never mind the fact that they look as though they're repelling and not attracting. That's not the issue. Feynman diagrams don't particularly represent attraction or repulsion. The particles are interacting. Electrons and protons come up from the bottom, they interact, and they come out again at the top. The point is that there are two forces at play when electrons scatter from protons. The electromagnetic force illustrated on the left shows the electron and proton coming in from below. They then interact by the exchange of a virtual photon, and they get some kind of change in their motion, in this case an attraction. The diagram on the right again shows the electron and the proton coming in from below, but this time the diagram represents the fact that they experience a much weaker interaction due to the exchange of a virtual Z0. Now both these interactions would be happening at the same time in an experiment where electrons are being scattered from protons. In fact, one of the early ways in which the presence of the Z0 was confirmed was by looking at this kind of elastic scattering of electrons by protons. The subtlety of the experiment was that the polarization of the electrons in the beam could be altered so that they either had spin plus a half or they had spin minus a half. If it's true that only left-handed electrons experience the weak force, then there should be weak and electromagnetic effects taking place for spin equals minus a half electrons. On the other hand, for spin equals plus a half electrons in the beam, there should only be electromagnetic scattering taking place. In the experiment that was done at SLAC in 1978, the physicists were looking for very small differences in the scattering when using left-handed and right-handed electrons in the initial beam. First they fired electrons polarized in one direction at the protons and measured what happened. Then they fired electrons polarized in the opposite direction at the protons and measured what happened. The difference was very small, about 1 in 10,000, but it was detected and it was shown to be real. The difference was because the right-handed electrons were only deflected by the electromagnetic force, whereas the left-handed electrons were deflected by both forces. By this kind of experiment, the presence of the Z0 was detected before it had ever actually been produced in the laboratory. In other words, it was confirmed that not only could the W plus and W minus transmit the weak force, which had been shown by other experiments at the time, and necessarily involved electrical charge being transferred as well, because we have W plus and W minus. Not only showed that, but also the weak force could show itself via the Z0 in situations where no electrical charge was transferred during the interaction. This is what physicists call the neutral current of the Z0. This experiment also demonstrated, of course, that in effect it was only left-handed fermions that had weak charge, and that fact is going to be important in our preparatory discussion as to why the Standard Model theory insists that fermions must be massless in and of themselves. On top of this idea of spin and weak charge, we're going to need to think a little bit more about the Dirac equation. This is the equation which all fermions obey and was formulated in 1928. It was the first theory to combine special relativity and quantum mechanics to describe the wave-like behavior of the spin-a-half particles called fermions. It looks complicated, but we may well be able to cut some corners and make it seem simpler. The field psi can be used to describe any fermion, those spin-a-half particles of the Standard Model like quarks and leptons. Psi is different from phi of the scalar field that we discussed earlier. The scalar field phi, if you remember, could be described by a complex doublet, although we didn't actually do our analysis with that full picture. We said that the scalar field phi could be thought of as having 4 parts to it: phi 1, phi 2, phi 3 and phi 4. Now, although it is very different from the scalar field, the Dirac field psi for spin-a-half particles, for fermions, can also be described by a 4-component function known as a Dirac spinor. We write it as a kind of column vector in psi 1, psi 2, psi 3 and psi 4. The 4 components this time relate to what we would call, or we could call, positive energy, negative energy, spin plus a half and spin minus a half. So a psi representing, say, an electron would contain information in it as to whether the electron was spin plus a half or spin minus a half, and whether it had positive or negative energy. Now, I know the idea of negative energy sounds weird, and it did to physicists in 1928. However, it's now understood to be simply to do with the idea of antiparticles. Negative energy states are taken to mean antiparticles. So the 4 components of the fermion field can now be said to relate to matter, antimatter, in other words particles, antiparticles, as well as spin plus a half and spin minus a half. But what a strange equation. It really looks complicated, but I suppose that's partly because it contains a lot of shorthand notations. Shorthand that's been added to make it look less cumbersome. We know, for example, that d mu psi, where mu can be 0, 1, 2 and 3, is really a 4-component space-time derivative. There are 4 bits to it. We also know that the square of that thing is given by these 4 things. We used that before. Of course, we have it here in the Dirac equation as being not squared, and this actually means that we have to keep the vector nature of it. 1 part in the x direction, 1 part in the y direction, 1 in the z direction, and 1 in the time direction, if I can use that expression. I won't write it out, just bear that in mind. There are 4 parts to delta mu psi, for mu equals to 0, 1, 2 and 3, namely for time, x, y and z. To complicate things further, of course, that gamma mu is a bit of an unknown to us at this stage. It turns out that it is a special set of 4 supervectors called matrices. Again, mu runs from 0 to 3, so there are 4 things. They are called the Dirac matrices, and this is what the four things look like. Even though these gamma matrices may contain mostly zeros and ones and i's, they have to multiply the four parts of the derivative in a special kind of way. If you've learned about matrices, you'll know what I mean. Otherwise, there's no way really we can understand this quickly, so let's just accept it. Things should come a bit clearer anyway as we move forward. So the Dirac equation has these four things: the Dirac matrices, gamma mu, multiplying in a special way depending on the value of mu. These four derivatives, delta mu psi, and psi itself is a thing with four parts to it anyway. So all the fours make sense. I suppose really this Dirac equation is more than one equation. And this shorthand just makes it look neat and puts it into one. We can't, as I say, deal with it properly in a short time, but perhaps we can try to take a simpler approach to it. We can try, for example, to simplify the Dirac equation a little by expanding out the derivative delta mu psi and ignoring the y and z components of it. If you like, we'll just work with time, which is mu equals 0, and space, which is x equals 1, mu equals 1 in the x direction. This means that the gamma mu could be simplified into a couple of matrices, and if we move them round a bit and call what's left of them alpha and beta, the Dirac equation can be written in this way: I delta psi by dt plus I alpha delta psi by bx equals m beta psi. Now, I hope that seems a little bit more reasonable. Alpha and beta are still 4x4 matrices, a bit like the gammas, containing mainly zeros and ones, but of course they have to multiply things in that special way, so you can't simply think of them as constant numbers multiplying things. Before we start to delve into this, to think about why the fermions must theoretically have zero mass, let me try and make this equation seem a bit more reasonable, to some extent at least. Suppose we had a particle wave, a fermion, only going in the x direction. And suppose it was massless. This is what we used to think neutrinos were like, before it was realized that they had mass. They were assumed to be purely a wave, no mass. Now if we assume that for the moment, and put m equals 0 in this form of the Dirac equation, and we rearrange things and we cancel the i's, we get this equation. Now this is very like a standard equation for a simple wave. It goes up and down with time, so it has a frequency, and it goes up and down with distance, x, so it has a wavelength, and the two are related by this constant, or rather matrix thing, alpha. Most standard wave equations that you may have seen before will probably have had double differentials in them in order to make one side equal to the other. You may remember that in school mathematics, for example, the double differential is needed because differentiating, say, a sine function twice gets you back to the sine function, and the same for the cosine. So we get equations like this. This would be a legitimate wave equation to describe the movement of most kinds of classical energy waves, such as light, sound, or heat. The velocity of the wave would be equal to c in the equation. Granted, the massless one-dimensional fermion equation of Dirac looks a little bit different, but I hope it doesn't seem too unreasonable. Anyway, I'm going to state the fact that the one-dimensional, in other words x direction, Dirac equation for a fermion with mass can be written as I d psi by dt plus I alpha d psi by dx delta psi by dx equals m beta psi. Remembering the fact that alpha and beta are not just numbers, they are 4x4 matrices. They multiply things in a more complicated way. Now, going back to the idea of spin, we know that fermions have spin which can either be along the direction of travel, plus a half, or opposite to the direction of motion, minus a half. We call them right-handed and left-handed. Turns out, however, that the matrix beta, which don't forget multiplies the 4 parts of psi in a special way, the matrix beta changes right-handed fermions into left-handed fermions and vice versa. Now that might seem strange, but it does. You'll remember that I said that the field psi has 4 components, 2 of which relate to spin. Well, when the psi on the right is multiplied in the special way by the 4-component matrix beta, it changes the position of 2 of the components in that column and effectively changes the spin from left to right or from right to left. This probably shouldn't surprise those of you who've done matrices before. Multiplications with matrices can shift things around. Anyway, if I write out separate equations for left-handed and right-handed components of the Dirac field using psi L and psi R, it first gives me these 2 equations. Now this is nothing new. I'm just saying, let's take the Dirac equation in the x direction, let's write it out for left-handed fermions, that's the top one. Let's do the same equation and write it out for right-handed spinning fermions. That's all I've done. Nothing new. However, remember that the beta, when multiplied out, changes a left spinning fermion into a right spinning fermion and vice versa. That means that if I then multiply out the beta on the right hand side of each of these equations, I'm left with this. Now that is weird. From these mathematical equations, it seems as though the left-handed and right-handed components are somehow mixed up. How can something on the left spinning one way be equal to something on the right spinning the other way? It doesn't seem to make sense. One way out of this, of course, is to suggest that the mass of the fermion is 0. Then the mass term on the right would disappear, and the equations would become, if I get rid of the i's, and there'd be no problem. A left-handed excitation could travel along, oscillating with time and space in proportionate ways, and separately, with a different equation, the right-handed excitation could do the same. There'd be no mixing of left and right in the equations, no complications. Taking away the mass got rid of that complication. But if the fermion has mass, let's go back to the idea of it having mass. Let's not give up on it just yet, although that is going to be where we're going. If the fermion has mass, the mathematics seems to give us a weird scenario where it predicts that the left-handed particle can somehow change into a right-handed particle and vice versa. Very strange. It's almost as though the fermion which has mass is changing from spin plus a half to spin minus a half as it travels along. That's weird. It's actually probably more accurate to say that the presence of the mass term on the right-hand side of the equation couples together the left and right-handed components of the particle in some way, but it's still weird. Now, even if you accept the idea that handedness could change over, and we could leave the mass term in and just accept that things are much more complicated than we can cope with, there's another reason why we should take the mass term out. What about weak charge? We said earlier that in effect it is only left-handed fermions that have weak charge, or that experience the weak force. Experiment has shown that to be true. So looking at the first equation, it implies that the derivatives of the left-handed component, which we know are involved with the weak force and have weak charge, must be equal to something multiplied by the right-handed component, which we know don't experience the weak force or have weak charge. These equations seem to be violating weak charge conservation. It's almost like having something on the left with electrical charge in it being put equal to something on the right without electrical charge mentioned. It doesn't make sense, and we wouldn't allow it. If we believe, as we do from experiment, that it's only left-handed fermions that have the weak charge, then these equations cannot be symmetric. weak charge conservation will not support these equations if only the left-handed fermions have weak charge. This means that we have just got to say that all fermions must be massless. We've got to get rid of the mass term in the equations in order to preserve weak charge conservation. The Dirac equation of fermions with mass would clearly mix the right-handed and left-handed components of the spin of the fermions, but if the right-handed and left-handed fermions have different weak charge, then the mathematics falls apart. So at this point, we have to accept that fermions, according to the standard model, must be massless. So that's that question sorted out. But of course the next thing to say is that we know that in practice the fermions are not massless. Theory is saying they've got to be, but we know they're not. So where do they get their mass from? Well, it turns out that they get their mass from the Higgs field, but not in the same way that the gauge bosons, the W's and the Z, obtain their mass. Okay, so let's move on and try to show how the Higgs field can give mass to the fermions. We've said before that most of the so-called fields of nature have their minimum potential energy when the field is zero. Even if they are multi-dimensional field, and here's one in 2 dimensions, they have a parabolic type shape and the field will be at zero at the minimum potential. The space around us, even empty space, is full of fields, and in general they have settled to a minimum potential, and the values of the fields are also zero. We have the electron field, the neutrino field, and other fermion fields. We have the photon field, the gluon field, and the fields of other kinds of bosons. We don't notice these fields in the vacuum until they are disturbed by some energy. And then we get what we call particles, which are really just excitations or ripples in those fields. In that case, when the field changes from zero, there is energy in the field, kinetic energy, and maybe, if mass is involved, potential energy. That kind of argument about fields, however, just looks at each field in isolation, assuming the energy that a field has is simply because of itself. We've written down Lagrangians, or rather Lagrangian densities of some of those free fields on their own. For example, the Lagrangian density of a simple scalar field was written as the kinetic energy per unit space-time, per unit volume of space-time, minus the potential energy per unit of space-time, and it was written like this. Now this has nothing to do with fermions, I just want to give it as a reminder. It was the Lagrangian for the scalar field of the Higgs, which we then made complex. The kinetic energy of the field involved derivative terms, the rate of change of the field with both space and time. This means that the kinetic energy of the field is to do with the stretching of the field in space and how it changes with time. The potential energy term involved the square of the field multiplied by a constant mu squared, and we said with that scalar field case, if mu squared is positive, it means that because we have a minus sign in front of the bracket, we have a minus term in the field squared, minus something times phi squared, and so it represents a real kind of mass. In fact, mu would then represent the mass. We have a U-shaped potential, and we could imagine a ball in a cup and all that kind of argument. The other terms in the potential energy, the quartic term, is to do with the extra energy involved by the fact that the field interacts with itself. It's a self-interaction term, and lambda is the self-coupling constant, the strength of the interaction of the field with itself. On top of those ideas, we went down the road of suggesting that mu squared could be negative for the complex scalar field, and this led us to a virtual mass, a ball on the hill, which led to symmetry breaking. We ended up with having a real mass in the valley, if I can put it like that, and the field, instead of being zero at this minimum potential, had a value of V. Now that was all for scalar fields, for bosons. When we come to fermions, for the Dirac field, the Lagrangian density is given by this. This was mentioned early on, but we didn't discuss it in any detail. But if Euler's equation is applied to this, it will actually give eventually the Dirac equation. Psi bar is known as the Dirac adjoint of psi. But for simplicity, just think of it as being such that psi bar times psi is psi squared, the field squared, a bit like the complex conjugate phi star phi for the scalar field. The gamma mu in the Fermion Lagrangian, as we said before, is what we might call a supervector, a set of four 4x4 matrices where mu, the index, can be 0, 1, 2 or 3. The Lagrangian density is for a fermion with mass. But since we now understand that the theory suggests that the mass of all fermions must be 0, we ought to get rid of the mass term, at least in theory, in which case the Lagrangian of a theoretical fermion field, such as that of the electron, must be given by this formula. This is really just the kinetic energy term. It may not look very sensible to us, but we should be able to appreciate that as it contains the derivative term only, it contains only kinetic energy, and it's for a fermion with no mass. However, there's something else to think about. Early on in our discussions, we touched on the idea that we can write down the Lagrangian of two fields together. Now that's not unreasonable, as there will be lots of situations where two fields will exist in the same place and at the same time. Two particles may be interacting, which means two field excitations are coming together. And here is the Lagrangian that we gave for the electron field and the photon field together. It essentially gives the Lagrangian density of an electron, which here has a mass term, but this time it's also coupled to an electromagnetic field, that of the photon, and as you'd expect, that's been written down without mass. We could call this whole thing the Lagrangian of quantum electrodynamics, because it involves electrons and photons. There's the electron Lagrangian, with a mass term this time, because it is dealing with real electrons as opposed to those in theory. That's what we've just been looking at. There's the photon Lagrangian, with no mass term of course, because photons are definitely massless. Remember, this F squared is really a funny mixture of derivatives squared, or subtractions of derivatives squared, of the electromagnetic vector potential A. But there's something extra here, an extra term, which must be some kind of interaction for the energy between the electron field psi and the photon field A. Something like this has got to be present in the Lagrangian of these two fields together, because we know that electrons are electrically charged and they therefore interact with the electromagnetic field. They repel one another and exchange virtual photons. There will be energy involved in this interaction, and so this term has got to be included in the combined Lagrangian of the two fields. We can't just have the free electron field, the electron particle, and the free electromagnetic field, the photon. We've got to have something in the Lagrangian that gives an energy from their interaction. In terms of the makeup of this extra interaction, if we ignore the gamma mu, we can see that it contains the photon field A straddled by the electron field psi. It also has a multiplier E in front of it. This E is known as the coupling constant, and its size will determine the strength of the interaction between the electron field and the photon field. It's actually the charge of the electron. Now, we haven't so far discussed interaction terms like this, but it probably should be obvious that if two fields are together and if they have something in common, like electrical charge or colour charge or weak charge, then there ought to be some kind of interaction, a term that has to be put in the combined Lagrangian, because the interaction will give potential energy. Their interaction will add to the potential energy of the system in some way and should be included, as I say, in the Lagrangian. It will end up being a negative something in the actual Lagrangian, because the Lagrangian is the kinetic minus the potential. Now, in relation to this idea, it was in the 1930s that a Japanese physicist, Yukawa, working in the context of nuclear physics, suggested that the extra potential energy from the interaction between a scalar field phi and a fermion field psi can be written approximately as V Yukawa equals G psi bar phi psi. Notice here we're now thinking about fermions, like electrons, interacting with some kind of scalar field or scalar particle. This is not electromagnetism now. We're going in a moment to end up thinking about fermions interacting with the Higgs field. Anyway, you can see the presence of the two fields in this expression for the interaction energy. The fermion field psi seems to straddle the scalar field phi, just like we looked at the interaction of the Lagrangian of quantum electrodynamics. The fermion field there straddled the photon field A. The important thing to notice about the Yukawa potential, as far as this discussion is concerned, however, is the G. This is the term that we're going to use for what is known as the coupling constant between the two fields, phi and psi, between the scalar field phi and the fermion field psi. The bigger G is, the bigger will be the interaction energy between the two fields. This coupling constant G will take different values for different pairs of fields. Let's face it, we have a lot of different types of fermion fields, various quark fields, various lepton fields, so they'll probably each couple differently to any particular scalar field. The coupling constant G is a measure of how strongly the two fields couple together, and it can be measured for various pairs of particles from the way they interact with one another. If, for example, we could imagine empty space with no disturbances, if all the fields were zero, then of course this extra potential term would also be zero. There'd be no interaction energy. Even if simply one particle, say an electron, was travelling through space, in other words, just one field was excited and all other fields were zero, then once again the extra potential energy would be zero. There would not be any extra energy because there would be no interaction. But hang on. What I've just said cannot be true. I said that if there were just one particle from a field that was disturbed in some way, and if all other fields were zero, and I went on to say that there would be no interaction with a particle like an electron that was moving along. That phrase, if all other fields were zero, can that be true? Ever since we've been discussing the Higgs field, we've come to realize that there is one field that is never zero, the Higgs field. We've learned that the Higgs field has some strange properties. It has a negative mu squared in the potential of its Lagrangian and a strange Mexican hat potential. It undergoes spontaneous symmetry breaking in order to minimize that potential, and from this it ends up with a non-zero value of the field throughout all of space. This means that whenever any particle travels through space, seemingly alone, it is not alone. Those ripples in its field will have to pass through the Higgs field. And if there is any coupling between the field of the rippling particle and the Higgs field, anything in common, then there will have to be an interaction term. There will have to be a coupling constant, and there will be an extra potential energy involved. So, when fermions like the electron or the neutrino or the quark or whatever travel through empty space, they are travelling through the Higgs field. And the fact that both the fermion field and the Higgs field are related to the weak charge, those fermions that are travelling will have to interact with the Higgs field. There will have to be an amount of potential energy of interaction involved, which will have to be subtracted from the Lagrangian of the system. The amount that will need to be subtracted will be given by the Yukawa expression G psi bar phi psi, where psi is the fermion or the electron field and phi is the Higgs field. Let me stress that. This kind of interaction applies to all fermions, quarks and leptons on account of the fact that they all relate to the weak charge. They all interact with the Higgs field in a vacuum. They may have different constants, g, but they will all interact in some way with the residual Higgs field. Now, before we add the negative of this expression to our total Lagrangian, remember potential energy terms are negative in the Lagrangian, we can to some extent simplify it. In the analysis of the complex singlet scalar field that we looked at, the complex field phi could be written in two ways, phi1 plus I phi2 or rho e to the I omega. We chose to analyse using the polar coordinate system where the two components of the field can be considered to be rho and omega. The omega component of the field went to produce the Goldstone boson, which disappeared, and the radial aspect rho is what we were left with. We had calculated the value of this field to be V, and we had a number of expressions for this in terms of things like the mass of the Higgs and lambda, the quartic self-coupling or Higgs self-interaction term. Now the same will be true for the more complicated complex doublet which we discussed but couldn't analyse. We said it would have a radial component to the field and not just one but three angular parts. These three would produce three Goldstone bosons which would be absorbed in some way by the W plus, W minus and Z naught to give them mass. They would disappear. All we would be left with would be the radial component, and this would fill all of space with its value of V. So effectively, phi, the field, which equals rho, the radius, will equal V. And it would be constant in all space. We don't need to think about those situations where a Higgs particle might be around, when the field goes up and down ever so slightly up the walls of the valley, and we'd have phi equals rho equals V plus H. We don't need to think about that. H is the oscillation of the Higgs particle. It can be positive or negative, but we don't need to think about it because H would be extremely small anyway. Even if a Higgs particle were around, we can still take the value of the Higgs field in this expression to be constant at a value of V. This means that when a fermion, such as an electron, passes through empty space, we can write the interaction energy as G psi bar V psi between the fermion field and the Higgs field. V is a constant. As a constant, of course, we can move it from in between the psi's and the expression becomes G V psi bar psi. Okay, so now let's add together the Lagrangians of the fermion field psi and the Higgs field phi using the complex singlet form for phi that we could just about deal with, the Mexican hat. And then we'll add to them the negative of this interaction energy. Don't forget, we're imagining a situation where a fermion is travelling through the Higgs field, so we need three bits to the Lagrangian: the fermion Lagrangian, the Higgs Lagrangian, and the negative of this interaction term. Here are our three representations of these in their most basic form before adding them together. We can whittle away at these and simplify them, possibly, from what we already know, and then we'll add them together to form the total Lagrangian and see what happens. The first of these, the Lagrangian of the fermion, must have no mass as far as the theory is concerned. We would like it to have mass to match reality, so we'll be hoping that some term in psi bar psi or psi squared will appear, but for now we'll get rid of this mass term. We've studied a second of these Lagrangians in some detail, and we know that it becomes, after symmetry breaking and after mathematical manipulation, L equals a half delta H squared minus lambda V squared H squared plus a half V squared delta omega squared. This is what we got after we went through the mathematics of the Mexican hat potential early on. We were left with the Higgs boson with a sensible negative mass term, which means that the mass of the Higgs particle is real, it's vibrating in the valley. We were also left with a Goldstone boson with no mass, or rather three of them if we could have done it properly. However, we know that the goldstone boson has been taken by the W and Z bosons in order to give them mass. So that is not going to be involved in our Lagrangian for the psi and phi fields. That means we can simplify that Lagrangian and get rid of that final term. So now, putting the three terms that we're left with together into one gives for the final Lagrangian of the two interacting fields, the Fermion field and the Higgs field, if you like, the electron travelling through the Higgs field, as this. Rearranging gives this. Now the right hand side is just the Higgs boson, which may be excited in the valley. The Higgs field, remember, is denoted now by H. It's got its derivative term and its mass term is negative, so the mass is real, all is okay. That Higgs Lagrangian bit has got to be around because the Higgs field is around, and it may be excited to give us that Higgs boson. So that's okay. The left hand side here is the Fermion bit. But now we notice that there is something that looks very much like a mass term present in its Lagrangian. It's a term in psi bar psi, or psi squared. So it would seem that the Fermion, which was required to be massless in and of itself, and which we made massless by only having the derivative term in the Lagrangian, has now gained a mass from its Yukawa interaction with the Higgs field. The Higgs field has given mass to the Fermion. Also, by comparing with the original Fermion Lagrangian, it's clear that m psi bar psi equals gv psi bar psi, and this new mass of the Fermion is given by gv. Now remember, V is something that depends on the Higgs field. It's the value that the field moves to in order to minimize its potential in the process known as spontaneous symmetry breaking. So it looks as though the mass of each of the fermions depends directly on this value V of the Higgs field, and also on some coupling constant G. We know, of course, that the masses of the various fermions are very, very different from one another. They vary widely from the extremely small masses of the neutrinos to the largest mass, which is that of the top quark. According to this formula, then, these masses can only be different if the G values for each of the fermions is different. This means that each of the fermions in our table couple to the Higgs field with very different strengths. They have different G's. The top quark couples to the Higgs field most strongly, giving it a large mass, and the neutrinos couple to it hardly at all. In fact, we can work out these coupling constants from what we know already. The value of V, the Higgs field, is known to be around 246 GeV, and the mass of the top quark is close to 173 GeV. So it's clear from the formula m equals GV that the coupling constant G for the top quark with the Higgs field must be a little bit less than 1. Here are some of the other fermions on our standard model with the strength of their coupling to the Higgs field calculated using this formula. See how small the neutrino coupling is compared to how large the top quark coupling is. So that's it. When a fermion travels through empty space, the vacuum, the field of which the fermion is really an excitation interacts with the non-zero Higgs field and produces what might be called a Yukawa potential energy. In the mathematical function which summarizes the dynamics of the system called the Lagrangian, this extra negative energy term is seen to be equivalent to the theoretically massless fermion having a mass equal to GV. That's it. However, let me have a final word on the Yukawa coupling constant and the Higgs. Even before the Higgs boson was found in 2012, it was realized from this theory that the Higgs particle being an excitation of the Higgs field in what we've been calling the valley, would couple most strongly to the top quark, because that is the most massive of the fermions, and the coupling strengths to other fermions would vary widely. The Higgs, as we've said, was discovered in 2012 at CERN in proton-proton collisions at the Large Hadron Collider. Protons travelling in one direction in the ring were made to collide with protons in the other direction at energies initially of around 3,500 GeV each. Protons colliding in this way will mean that up and down quarks will collide, and also gluons from each proton will also collide. The coupling of the up and down quarks to the Higgs field is small because their mass is very small, so that the chances of a Higgs particle being produced from up-down quark collisions is very low. Protons only contain up and down quarks, nothing of any higher mass. However, it is possible that at these high energies, gluons from within each proton can interact with each other and can convert to a top-antitop quark pair. The gluon from the left here produces a top quark and an anti-top quark. As the coupling of the Higgs field to the top quark field G is large, there's a good chance that a top quark from one gluon will annihilate an anti-top quark from the other gluon and produce perhaps a Higgs boson. The other top-anti-top quark pair are shown here diverging. Of course, they can't be free particles and travel away as shown. In fact, they will actually annihilate one another. Rather than drawing it like this, with the two outer top and anti-top quarks seeming to diverge, this kind of interaction is usually shown with what is called a top quark loop diagram, the triangle where the two gluons are shown combining to form a loop of virtual top quarks. This whole process is known as gluon fusion. Consequently, we can say that this process consists of a top quark and an anti-top quark coming out of the vacuum because of the gluons, as they couple well to the Higgs. In other words, they've got high masses, they couple to the Higgs field. They then produce a Higgs particle. There are other gluon fusion processes like this which are possible, but this one, with the high mass of the top quark, is perhaps the most common. The production rate of Higgs bosons at the LHC was approximately 1 in 10 to the 9 collisions. So only 1 out of every 10 to the 9 collisions of protons actually produced a Higgs boson. Once produced, the Higgs has a very short lifetime and decays within about 10 to the minus 22 seconds. They decay in lots of ways, but in the main, they decay into bottom-antibottom quark pairs. And these then proliferate into more particles, into more hadrons, into normal kinds of and exotic kinds of particles. The decay products from the Higgs would be therefore difficult to detect on account of this multitude, this proliferation of debris from the proton-proton collisions. In order to know you've found a Higgs, you need to know that you've detected clearly its decay products. So there would seem to be a real problem. However, out of the many ways in which the Higgs can decay, the best candidate for detecting its decay products was considered to be via its decay into two photons, which happens only around 1% of the time. Only about 1 in every 100 Higgs particles produced will decay into two photons, so it's very rare. Of course, photons are massless, so in the standard model, the Higgs boson doesn't couple to the photons, so it's not a straightforward decay into two photons. Instead, the decay of the Higgs into two photons occurs through what is known as a loop-mediated process. Once again, there are lots of possibilities, but here are two main routes. The larger contribution of these two is from the W boson, and the other, which is probably about 5 times smaller, is from the top quark. Here's the diagram for the top quark route for the decay of a Higgs into two photons. Again, it shows a loop of virtual top quarks. The Higgs comes along from the left and eventually ends up as two photons or gamma rays. As mentioned, this photon-photon final state is very rare and in some ways quite fortuitous. What I mean is, the Higgs is neutral, no electric charge, so it has no reason to couple to the electromagnetic field of the photon. On top of that, the photon is massless, so it has no reason to couple to the Higgs. We only get this two-photon outcome because it is mediated by the virtual particles like the top quark in this diagram, and in others, as I said, including the involvement of a W boson. There were two experiments at CERN that looked at the two photon decay products coming from the proton-proton collisions at different energies. One was called the Atlas experiment and the other CMS. Here is some of the data from the CMS experiment. This shows what is called the combined two-photon mass spectrum. If no Higgs particle had been created, the top graph would show a smooth, continuous curve of essentially random events for two photons, with the combined energy shown on the x-axis. It would follow the dotted line, nice and smooth. It can be seen, however, that there is a fairly clear excess of events at the combined energy of around 125 GeV, the little bump on the curve. Taking away the background slope and making it flat gives the data shown in the lower box. This was the early evidence for the existence of the Higgs boson at mass around 125 GeV, before all the data had been taken. So that's it. End of story. Many corners have been cut in the 6 videos that have tried to explain how the Higgs field gives rise to the masses of the elementary particles, but hopefully it has allowed some people to appreciate just a little of how special the Higgs field seems to be. However, if you've worked at understanding the arguments, you should have a reasonable grasp of the physics as it is presently understood, and be aware of more or less where the corners have been cut in these arguments. In both cases, in giving mass to some of the gauge bosons and in giving mass to all of the fermions, it involved starting with a Lagrangian with no mass, because the theory said it should be massless. This was in the form of simply a derivative. Then, either by the process of symmetry breaking in the case of the gauge bosons, or by interaction with the Higgs field after symmetry breaking in the case of the fermions, a new and extra mass term appeared which changed the Lagrangian from being that of a particle with zero mass to being that of a particle with mass. Now all I can say is that if you want to understand all this in more detail, then you'll need a postgraduate course in quantum field theory.